All right, everybody. So I was in the last video talked about writing your own exponential word problems and writing your own quadratic word problems. So here's the video about quadratic word problems. The Probably the most surprising thing about quadratics is that they can be used to describe things that are very different from each other. Quadratics started as area problems. Quadratic is like a four-sided shape, and then it also came about hundreds of years later that they could also be used to describe something flying through the air. And those are usually the two places where I draw my word problems for quadratics from are either trying to find the area of some sort of a shape or trying to figure out something flying through the air. So I'll show you an example of one of each. So let's do the classic example of an area problem, which is, let's say that you have a barn. This is the barn, and you want to build the best possible little zone for your little petting zoo of sheep here. And so you've got some fencing and you want to enclose the biggest area for your little sheeps. So you've got 100 feet of fencing and you want to maximize the area. But the nice thing about a barn is you don't actually have to have fencing along this side of the barn. So really it's a three-sided fence. Just the three sides. Let's use a different color. Let's say we just need to find just the three different purple sides of the fence. And so let's say I don't know how long this is. I don't know how long this is either. But you have 100 total feet. And so this other missing side is 100 feet minus the two sides that I put up there. And in here, my sheep, they want the biggest possible area. And so the way to find the area is just like length times width. That's where quadratic equations came from, was from length times width. And so what I'm going to do is set up an area equation. The area of my sheep zone is x multiplied by 100 minus 2x. And this right here, if I type this equation in, x times 100 minus 2x, we get a nice beautiful parabola. Let's zoom out so we can see it a little bit better. There we go. And I want to use this information to try to figure out how I can create the biggest possible pen for my sheeps. So I can see that somewhere in the middle there's a vertex. And the thing that's pretty obvious from the graph and somewhat obvious from the equation are my two x-intercepts. I can see from here that x equals 0 will make the fence 0. I mean, obviously, if you don't go anywhere away from the barn, you don't have anywhere for your sheep to go. Now 100 minus 2x is a little bit harder to find the x-intercept. So if I set 100 minus 2x equals 0, I can add 2x, getting 100 equals 2x, and divide by 2, getting 50 is x. And that means that x equals 0 and x equals 50 are my x-intercepts. And so then you should be able to realize now that the vertex is going to be halfway in between those. And so halfway in between 0 and 50 means that my vertex is at the point 25 comma something. And I can get that something by plugging 25 in to the area right there and right there. So the maximum area is going to be 25 times 100 minus 2 times 25. And that gives me 25 times 100 minus 50, or 25 times 50. So let's go ahead and use Desmos to do the work for you. 25 times 50. Oops. Something else. 25 times 50 is 1250, and so that should be the maximum area. So there's one sort of example of a word problem. If we zoom out just a little bit more, we'll see it soon enough. There's our vertex right there, 25 and 1250. So one type of a word problem, you can do some sort of variation on fencing with a barn. Maybe two sides are used. Maybe you have a different amount of fencing. Maybe there's some other parameters there. But different problems with area are a good idea for quadratics. The other type of word problem that we've done a lot of is something flying through the air. So let's say that we have just a situation of something flying through the air where it jumps from, let's see, it jumps from a 10-foot platform, maybe you're diving, reaches, let's say that you got a lot of vertical, so it reaches 13 feet in 0.5 seconds, and maybe you're diving, so the question would be something like, when will you hit the water? So this is a classic sort of word problem. So jumps from a 10-foot platform, reaches 13 feet, and I'm going to make it clear that this is the maximum of 13 feet in 0.5 seconds. So then to take that, you're going to use your vertex form where it reaches a maximum after 0.5 seconds. So that's your h value, and a maximum of 13 feet. That's your k value. And then you're going to use the initial amount, the jumping from a 10-foot platform, to solve for a, just like we've practiced several times. And so then this gives me -3 equals a times 0.25, because I squared 0.5. And that would mean a is equal to -12. Pretty close to being accurate, not quite. It should be 16. But it's good enough for this video here. Maybe there's some weird air resistance going on. You got crazy swim trunks on or something. So then if you type your equation in, -12 times x minus 0.5 squared plus 13, go back to my zooming, my normal zoom, you can see the vertex is just like I said it would be, the y-intercept is just like I said it would be, and then you want to find out when it hits the ground, which turns out to be 1.541 seconds if you solve it by graphing. Or you could go back and solve it by hand, where you set your original equation equal to 0. So just taking away 13 and dividing by -12, etc., etc. Taking the square root of this and then adding 0.5 to it. And after all that work, turns out you're going to get 1.54. So thanks for watching. Please ask questions or comments if there's anything else I can do to help.